We are discussing the deformation of axially loaded bars in this video. So that this video is about deformation. Of axially loaded bars. When the deflection of an axially loaded member is a design parameter, when you design something and one of the design parameter is the deflection of an axially loaded member, then it is necessary to determine the deformations. Axial deformations are also required in the analysis of statically indeterminate bars. It is also to be noted that the deflection characteristics of bars provide necessary information for determining the stiffness of systems in the analysis of mechanical vibrations as well. So when you consider the deformation of an axially loaded bar, we are talking about a bar which is loaded axially. So you have like this, you have a load here. You can have the bar either fixed here or a load acting at the other end. Let's say a force of F Newton acting at either side. So in order to analyze the deformation of this bar, we consider as in every usual engineering analysis, we consider a small strip. So let's consider a strip here and let's call it dx. And on application of this load, let's say there is a deformation of, let's say this strip has been deformed like this. So there is a change in length of that strip. Let's call the total change in length is du. The sum of these changes, let's call it du. Now we know the strain is change in length over the original length. So we have a strain due to the applied load is epsilon in x direction is equal to du over dx, and from that you can calculate du is equal to epsilon x dx. So this is the change in length or increase in the length. Now if the length of this the whole bar is say L, then if you integrate this condition, the change in length of this strip over the entire length of the bar, then you can calculate the total deformation of the bar under the applied load. You also have a relation between stress and strain that gives you stress over strain. Stress by strain is a constant. We have discussed that in Hooke's law in a previous video, that stress over strain is equal to Young's modulus, and you also know that stress is force over area. In this case it is F over A. So you can substitute this equation. Rearranging this equation, you have epsilon is equal to sigma over E, which is stress over Young's modulus, and you have sigma force over area. Therefore you have substituting sigma by F by A, you have epsilon or strain is equal to F by A E, which where F is the applied load, A is the area of cross section of the system on which this load is applied, and Young's modulus E is the Young's modulus of the system. So in order to find the total deformation, you integrate this over the complete length. So the total elongation is integral 0 to L du is equal to integral 0 to L epsilon x dx, and substituting epsilon x, you have is integral 0 to L f dx over a. So integral 0 to L dx will give you, that is equal to f by a x 0 to L, that is fl over a. So that's your equation for deformation of axially loaded bars. So what we have discussed here is a load acted upon by a system, or a bar acted upon by a load F. The total length of the bar is L, and we considered a small strip here, this strip here, and that has been elongated by a distance du. Now we know the strain is change in length over original length, so the strain on that particular strip that we considered here is du over dx, and from that you can calculate the change in length of that particular strip, that is du is equal to epsilon x dx. We also have stress over strain is Young's modulus, and the stress is force over area. In this case it is force F over area of cross section of the bar, and you can substitute this equation or this relation in this equation, and you can get epsilon equal to sigma over E, whereas sigma is F by A. So you have epsilon strain is equal to F by A. Now substituting back that relation in here, you have total deformation is integral 0 to L du, that is equal to 0 to L f dx over AE, and on integration you get x within limits 0 to L, that is FL by AE. You can also write it PL by AE, which is there are different cases, there are different notations. PL by AE, it's both the same, essentially the same thing. P and F are the applied load in Newton. The unit of this equation will be Newton times meter over meter square over Young's modulus. Unit of Young's modulus is Newton per meter square. So you have Newton meter square, and the unit of PL by AE is the length unit, meter or millimeter. We will discuss in detail deformation of an axially loaded system in the next video. Once again, thanks for watching.